All right, we are going to start. We're going to start by you doing a calculation of the pH of the solution. It's going to be a really easy one. This is meant to be a confidence booster.
It's going to destroy your confidence.
If we have a 0.20 molar acetic acid solution, could you please calculate the pH? Okay? Told you it was easy.
Think this out there. It's not fall for the trap.
Now I would ask that you write the equation and the expression. And I already have an answer, by the way. Took me 12 seconds.
What's the value?
You get triple time, so it should take you 36 seconds. Done yet? Bridget, you done? What'd you get? 2.72. Yeah, that's what I got. $2.72? Are we in agreement? Okay. And that is correct. X squared over 0.2, and you get pH equals 2.72. All right, so here's my question. This is a conceptual question. If I were to add to this solution, sprinkle in some solid sodium acetate. All right, so we're going to add solid sodium acetate. My question is, and I would like for you to chat with somebody nearby you for a moment, and I want you to make a prediction, not a guess. There's a difference between a prediction and a guess. Prediction is supported with an explanation, a guess is not. And I would like for you to predict what will happen to the pH of this solution upon the addition of sodium acetate. Will it go up? Will it go down? Will it stay the same? Or is it impossible to determine based on the information provided? Discuss.
So this is all that raises the molarity. Now it does? Therefore, the negative log of the lower value would be
You're adding a base.
yeah, it would be pH would be high.
You're adding a base, so
So it becomes closer to 7.
There's a safe strategy.
Think about it like mathematically.
All right, we ready?
Yeah, shifting left, therefore.
We're gonna vote.
Value is lower.
Everybody close your eyes when you vote. No cheating, close your eyes. Kevin, close your eyes. Raise your hand if you think the pH will increase, decrease, stay the same. Cannot be determined. All right. Thank you. May open your eyes. Everybody either said increase or decrease. Nobody said stay the same. Nobody said impossible to determine. All right. The answer is increase. So those of you who are celebrating, the only thing I know for certain is that you guessed correctly. I do not know if you predicted correctly. So give me an explanation, and then I too will be impressed. Who's up first? All right, Jake. There are a couple of ways that you can explain this. So go ahead.
That's the right answer.
So when you put the solid in solution, it'll associate increasing the acetate ions, and that'll, through equilibrium, shift to the left. The Q value will increase, so shift to the left, and there will be less H plus ions.
Okay, so Jake took a Le Chatelier's principle approach. Very good. The addition of acetate ions will cause the equilibrium to shift to the left, which will effectively remove hydrogen ions from the system, and it will raise the pH. Very good. Did anybody come to the increased pH conclusion for a different reason? Kevin. Okay, very good. That is another way you could have done the same thing. If you look at sodium acetate and you say, well, this is a basic salt, so if I add a base to anything, what happens to the pH? It goes up. All right, so the addition of a base will absolutely increase the pH, but it also but what it does, this is kind of really how it does it, is by shifting this equilibrium to the left. Either way you look at it, we result in a higher pH. So far, so good? All right, now let's do some math. So let's say this is 1 liter, and what we added was, we added, say, 0.09 moles. All right, we added 0.09 moles of sodium acetate to this 1 liter solution. We are going to make an assumption that the addition of this solid does not change the volume of the solution. It will still be a liter. So we don't have to contend ourselves with dilutions or anything like that, at least not yet. Okay. 0.09. So effectively what we now have is a solution that is 0.2 molar in acetic acid and 0.09 molar in acetate. That's our solution. So calculate, please, the pH of that. Now, I know there are people whose initial reaction is, I don't know how to do that.
Ice,
And I would submit to you, you absolutely do know how to do this. You do this is equilibrium. Now, I would not approach equilibrium making assumptions and automatic thinking your calculations. Think it through. I will do the same. I'll get done before you. So I am done. I didn't confirm my answer, so. Yes, I do. Are you done, Kevin? Yes. That's the answer I got. Could be right, I could be wrong. Yeah, that's what I got. You're wrong, Kevin. My answer's been confirmed.
Jake got it.
Unless we're both wrong, we did the same wrong thing. Luke, you done? Very nice. Got a third one. It's not looking good, Kevin. Maybe you should take another stab at it. What do you think? Instead of sitting there going, nope, I'm right. The whole world's wrong. Who else has an answer? Tell me what that second number is. Correct. All right, there's another one.
I think I'm wrong. I'm going to show you anyway.
All right. Maybe you should think you're right. I vote for confirmation. You are correct. Look at that. Have you done it again yet? What an idiot.
What a, great student. Hasn't figured out how to do it.
Jump right to the formula, made an assumption, no ice chart, no reasoning. Oh, it's gotta be x squared over, because that's a rule. Just like before.
I had the equation and I started to erase and I didn't.
You treat this as if it's a fact that you have to pull out of your brain. It's not something you have to figure out.
See, Kevin,
But now I've spent 3 months on equilibrium and every calculation is just x squared over the number given in the problem. That's not what it is. Thank you, you like that. Yeah, hint, hint, it's not x squared over the number in the problem. That's not how it works. That's a knee-jerk way of doing it in equilibrium. That's not thinking. All right. The answer is 4.4.
Ah.
All right. What is the initial concentration of acetic acid? 0.2. What is the initial concentration of hydrogen ion? What is the initial concentration of acetate ion? 0.09. Hey, that's it. The rest of the problem is just business as usual. That's it right there. You cannot just put 0 there because that's a rule. It's not a rule. All right? It's if you put acetic acid into water, what is the initial concentration of acetate in water? 0. What is the initial concentration of acetate in a solution of sodium acetate? Not 0. All right, there's the acetate ion is present in the solution. There is acetic acid in the solution, and there's acetate in the solution. Prior to any ionization, there isn't any hydrogen ion yet. That remains 0. It ionizes. Equilibrium is established. It's going to supply that X quantity. All right, so we'll have X hydrogen ion. All right, we will also increase the acetate concentration as the acetic acid ionizes. It's going to make more acetate. All right, an additional amount of acetate will be added to that 0.09, giving us 0.09 plus X. Now, when we go to plug in, we have taken the position that this minus X, since it's going to be a small amount, is not going to significantly alter this number so that we can ignore it. Well, you know, I mean, if I can ignore it in a subtraction, I can ignore it in addition too. So we will continue to use that same practice of saying that X value is going to be small enough where it's not going to significantly change. So when we do this calculation, I want to point out it is still the identical equation. it is still the identical expression. It is still the identical K value. The equilibrium system hasn't changed. All right, what's different is that there was acetate ions in there from some other source. So when we go to plug in, it's not x squared because they weren't both 0. It's x times 0.09 over 0.2. Solve for x gives you the hydrogen ion concentration, get a pH, and I think it was 4.4. Is that what it was? 4.4. And our original prediction has been mathematically confirmed. The pH did in fact increase. Whether you want to look at it as a equilibrium shift, whether you want to look at it as the addition of a basic salt, either way, we have a pH that has gone up. What do you think? Want to do another one real quick?
Just do 5
One more.
real quick.
All right. Aminoweak acid.
Acetic.
Now let's. Now let's, how about we do a base? Let's do a aminoweak base. All right, let's do a mount. Nah, we'll do it. Go to your KB table. Get something good.
Let's do Trimmer, how about lime?
Dimethyl.
Only if you can pronounce it properly. Trimethylamine. So that would be. Is that CH3 taken 3 times NH2? Just N. CH3 taken 3 times N?
Yeah.
Okay. Now, actually that makes sense. All right, now, I need, all right, impress me now. I need a salt of the conjugate acid of this base. All right, I need a salt of this conjugate acid. But the anion needs to come from a strong acid so it doesn't interfere with our pH calculation. So let's agree that the anion will be chloride. All right, so what will this be? The cation. It's going to be a chloride. So what's the cation?
H, NH, or
Yeah, where are we going to put the H?
at the end.
Right?
What? Wait.
Oh, we never put the H in. 3. Now I don't have enough. There we go. Squeeze that in there. Right? All right. Adriana, give me a volume. How many milliliters you want? 28 milliliters. Bonnie, what's the molarity? 0.4 molar. Luke, how many milliliters of this one you want?
700.
Now be reasonable.
24.
24 milliliters. Paul, what's the molarity?
0.2.
0.2. All right, there we go. Here are our 2 solutions. These are 2 separate solutions. We mix them together into 1 beaker. We measure the pH. What will it be? Got it?
I need some time to digest this one.
No, you don't.
Wait, what are we looking for?
The pH of the combined solution. Kevin, come on.
You understand equilibrium, you can do this.
I will. I say speak.
Do I have to dilute?
What's this? Dilution calculation.
I would advise a dilution first, yes.
You're gonna mess around. We do not. Alright.
I'm gonna put my answer up.
I'm just starting to comprehend as well.
What's the comprehend? Write the equation, write the expression, look up the value. And I would like, I'm hoping somebody will get my answer, so we confirm it. I don't know. I'll do it again, actually.
I got 11.1.
I got 10.2.
Yeah, I got that.
Why does that mean?
Oh, well, one thing's for sure, I didn't use the right K value. What is the K? I can't even read this paper. That's definitely not what I used the first time, I don't think. Maybe I did, I just don't remember.
Wait, what's the 10.2?
Jake, what do you got?
Oh, wait, why? I used the wrong
Alright.
value. Why did I just look at, what? This?
Divided by 0.0923. 0.0923.
Hold on, boy.
All right, I did get a different one.
Where's the other guy?
I got 0.17.
We consulted over here.
10.17. Everybody get that one?
Yeah.
All right, cool.
I'm stupid.
Oh my gosh.
All right, so in this case, the first order of business is to do the dilution. All right, it does have to get diluted to a volume of 52 milliliters. And when you do the dilution, up here in blue, I wrote the diluted molarities. So these are the numbers we have to work with. But you know how to approach it. It's still we still have to write the equation. We can take that weak base, add the water, move your proton. So CH3 taken 3 times, NH plus, get your OH minus, which means it's going to be a KB. So the KB will be that cation times hydroxide over the weak base itself, the trimethyl, I guess, amine. All right, and the KB was 6.4 times 10 to the negative fifth. All right, so when we go to do our values, all right, the weak base is 0.215, the cation is 0.2 or 0.0923, and what we're trying to find in this case is hydroxide. You plug in and solve, get hydroxide, you get POH, subtract from 14, you get 10.17. What do you think? All makes sense now? All right. What you just did, all right, the solution that was prepared and the calculation you just did, that solution is called a buffer. All right, this is a buffered solution. It is arguably in the world of AP chemistry, if you polled everybody in the country, teachers and students alike, who take AP chemistry or have ever taken AP chemistry and ask them the question, what is the hardest thing in AP chemistry? I guarantee you number one on the list would be buffers. All right? It is not number one on my list. It is most definitely nowhere near number one on my list. I don't find buffers to be any different than anything else, truthfully. And I hope that you also, if you were able to do that, all right, say, what's the big deal? Right? Now, there are some conceptual aspects of buffers that are a bit challenging, okay, that we have to look at. But as far as the math goes, if you were able to reason through that, then you're good to go. That's as hard as it gets. All right, but what a buffer is, how it works, and what its purpose is something we do need to spend a little bit of time with. All right. First and foremost, the function of a buffer. I'd like to know your thoughts, because this is probably not, in fact, I guarantee you, it's not the first time you have encountered buffers. Probably the first time in chemistry, but I know for a fact buffers come up in biology. Leo.
This might be wrong, but as I
As soon as
remember,
you always say that, you preface everything by assuming it's wrong.
as I remember,
Okay?
buffer resists changes in pH.
That is perfect. That is a textbook definition. You are a good memorizer. Good job. Good job. Everybody get that down? A buffer is a solution that resists pH changes. Okay? Is a solution that resists pH changes. That is the function of a buffer.
This solution, this 52 milliliter solution is the buffer.
This entire solution is a buffer. I wanted to put up the, it's starting to go. I want to put the packet up on the screen. You can go to it. My computer is going very, very slowly at the moment. All right. Let me put this up. So this is page 8. Page 8 of your packet. So a buffer, again, by definition, is a solution that resists changes in pH. That's what it does. That's what it's for. That's its function. The reason why buffers are important. There are a lot of chemical reactions that are pH dependent. A lot of solutions or solubility is influenced by pH. A lot of the chemical reactions in the body are influenced by pH. That if the pH gets too high, the reaction will not proceed efficiently, or if it gets too low, it will not proceed. So it needs to be in a certain pH range. Remember when we did redox reactions, we had to balance, balancing redox, whether it was in an acid or a base. And you had to add water molecules to balance the oxygens, and you added hydrogen ions to balance the H's and electrons. Remember all that fun stuff? Yeah, just pretend. All right. But those redox reactions themselves had to either be in an acidic solution or a basic solution. And the reason for that is because these were reactions that are pH dependent. Right? They don't function if they're not in the right pH range. Human body, with the exception of your digestive system, which is acidic, most of your digestive system, the rest of your body falls in the neutral pH range, somewhere between 6.8 and 7.2. And largely because many reactions in your body function in that pH range. And if your pH gets too high or gets too low, then those reactions cease to function, and they can can have some significant medical impacts, you know, because of pH balances. It is one of the things in the body of, you know, examples of homeostasis, you know, maintaining a balance. Remember homeostasis? Homeostasis is the biology word for equilibrium, all right? Maintaining a balance. Your body temperature is homeostatic. You maintain a relatively constant body temperature. But pH is also something that has to be maintained. A buffer is how that happens. All right? A buffer is used when the pH matters. All right? When the pH matters. So this picture is meant to illustrate or distinguish between a solution that is buffered versus a solution that is not. So just look at the diagram for a second. You start off with water, you know, neutral, pH is 7, and we add some sodium hydroxide to that, specifically 5 milliliters, 4 molar, and the pH jumps up to 12.3. All right, not an unsurprising climb. Adding a strong base like sodium hydroxide to water, we would expect to get a high pH. All right, but if you were to add the identical solution, the 5 milliliters of sodium hydroxide, to a buffered solution, it's still going to go up. All right, you add sodium hydroxide to something, the pH is going up. There's nothing you can do about that. But it only goes from 4.74 to 4.8. It increased by 0.06 compared to doing the same thing to water, increased 5.3. That's a thank you buffer. That is the role of a buffer, is to resist, and the word is resist. It resists, it does not prevent. All right? You have a buffer in your blood that will control pH. It's actually it's a dueling equilibrium. It's carbonic acid. So it's this bicarbonate ion, but that also is in equilibrium with carbon dioxide and water. So this one reaction in your body, mostly in your blood, is the homeostasis for carbon dioxide. It maintains carbon dioxide balance in your blood. It also maintains the pH balance in your blood. If you hyperventilate, what is the standard treatment for hyperventilation? Put a paper bag. All right. When you hyperventilate, you are breathing so rapidly that your carbon dioxide levels plummet in your body. All right, because you're just constantly exhaling and you're not replacing it. Your CO2 levels drop. Well, if you take CO2 out of the system, what happens to the equilibrium? The entire thing shifts to the left. So when you hyperventilate, it also pulls hydrogen ions out. The pH of your blood starts to climb. All right, that is the largest concern about hyperventilation, is actually your blood starts to get a little basic. All right, so by breathing into a paper bag, you are artificially increasing the carbon dioxide concentration in your blood, shifting this equilibrium back to the right. Crying babies, constant hysteria causes the same thing to happen. So it's there's concern there, but this reaction shifts back and forth will help regulate hydrogen ion concentration and carbon dioxide levels in the body. It is a buffer. All right. So that is the function of a buffer, is to resist the pH change. Now, what is a buffer? There are 2 ingredients. Write this down. There are 2 ingredients to a buffer. It is, and there are 2 types of buffers. Okay. So it could be one type of buffer, call it an acidic buffer. I don't know if that's really proper. I call it an acidic buffer. But the 2 ingredients would be a weak acid and a salt of its conjugate base. first problem we did was acetic acid, sodium acetate. Is that right? That would be an example of this. Acetic acid and a salt of its conjugate base, sodium acetate. Both of them in the same solution. You can have a basic buffer, that was the one we just did up on the board, is a weak base, and you tell me what to put for the rest. A salt of its conjugate acid. If these two chemicals dissolve together into the same solution, okay, to make a buffer. It has to be a weak acid, it has to be a weak base, or a weak base. You cannot use strong acids and bases, because they do not have an equilibrium system. There is no shifting that can happen. All right, so the idea, all right, if we look at this picture right now, I don't know what time we done. 18. All right, good. If we look at this picture, and then we will start with this tomorrow. But I want to show you right here. Don't pack up. Right here. This is indicating kind of like it says your initial. It would be like I have 1 molar HF and 1 molar sodium fluoride dissolved in the same beaker. I have an acid and I have a base, both present in the beaker. So that if somehow some source of hydroxide ions was introduced to this buffer, all right, it will actually react with the HF as opposed to in water, it just makes the pH climb. All right, so the components of the buffer will actually react with and consume anything that gets added. Homework is up on the whiteboard. There's nothing about buffers in the homework. Have a good day. Wouldn't that be funny if you discovered that it